This is One Universe at a Time. I'm Brian Koberlein. Quantum computing has the potential to revolutionize technology. Quantum particle states, called qubits, would take us far beyond the processing power of zeros and ones. But qubit processing is based on probability, not certainty, which means every answer you get might actually be wrong. On our show today is Dr. Ed Hach, an assistant professor of physics at the Rochester Institute of Technology. He's going to tell us how to make sense of data generated by qubits and explain how it could be useful and how it might not. So I understand one of the areas you're looking into is quantum information. And I know a lot of times when we think about information, we think maybe about computers, ones and zeros, binary information. How does quantum information differ from that?
Classical information is typically encoded in bits. And a bit is really just anything that can have two different distinct values of some physical variable. Maybe it's a voltage or something like that. And so we normally just canonically call one of them a 0 and one of them a 1. It doesn't even matter which one you call which, just that they're distinct. And so any code that runs on something like a computer, any of the computers in this room, for let's say, is really just a long sequence of ones and zeros that are arranged in a certain way to convey the information that we want to convey to one another. And to process that information, we use physical systems like electric circuits and whatnot to alter and flip and rearrange the ones and zeros, often conditional on other ones and zeros. So quantum information allows us to do two things that we can't do in classical information. One of them has to do with the so-called principle of superposition, which basically is something that says that quantum mechanical systems can get into two what might seem like mutually exclusive states at the same time. Now, that's a misinterpretation. They can't actually do that. It has to do with something called quantum indeterminacy, or what people normally call quantum uncertainty. So let's imagine that our bits are yes and no, mutually exclusive things. Classically, we expect if we ask a question of someone, the answer is always yes or no. Or perhaps if we ask a question and they don't know the answer to that question is still yes or no, we just don't know, so we have probabilistic information about it. Maybe it's yes and maybe it's no. Quantum mechanics is different. Quantum mechanics allows things, physical systems, to get into a state that is neither yes nor no, but it's a true physical state of maybe. And when you have something that can get into a true physical state of maybe, because of the way the rules of quantum mechanics work, it means that it's almost as if a quantum information carrying bit, which we sometimes call a qubit, can encode all of the possible outcomes to a problem simultaneously, or it can encode all of the possible outcomes for that particular qubit in a way that's simultaneous in a manner that classical physics just can't.
The quantum information system, because it's basically a potential, it's all the different possibles of maybe.
So if you imagine a range between yes and no, in classical physics there's no range between yes and no. It's
right,
yes
it's either
or
yes
no.
or no, and that would be the binary.
And so a quantum system, if it's left to itself, and that's important, can actually be in some, we call it linear superposition, or think of it as just a combination of yes and no. The way I describe it in popular talks is, imagine that you were going to ask someone out to dinner. You go and you ask them out to dinner. You say, would you like to go out to dinner Saturday night? And the person says either yes or no. They might even be lying, but the answer is yes or no. In quantum mechanics, you might ask, in that scenario, you might ask somebody out to dinner and they would say 1 over the square root of 2, yes plus no. Or what they probably say is maybe. Mm-hmm. But it's a true maybe. In other words, the answer doesn't really even exist at that moment. That's good news for quantum computing. Here's the bad news. The bad news is that if I want to actually get an answer out of my quantum system, I have to measure it. And when I measure it, me, big clunky me in the classical world, comes in and invasively probes this quantum system, and I force its hand. In other words, I show up at the door at 6 o'clock on Saturday night, and I say, so are we going out to dinner or not? And then the answer jumps from the indeterminate quantum mechanical maybe to a very definite, let's pretend yes.
Okay.
So there's a complex interplay between this idea of a qubit that can have an indeterminate state, meaning a state that's somewhere between yes or no.
In some sense, then, if you're going to calculate with ones and zeros, if you did it with, say, a mechanical device or a computer or something, then at any given point, you could see what the state of the system is. You could see what's happening in your computer, and your computer can still function.
This is in the classical.
In the classical sense. But a quantum computer, it can do whatever calculations it's going to do, but as soon as you look at it, as soon as you observe it, you broke your computer.
That's right.
You get an answer, but it's a trick you can only do once.
That's right, and that's one of the limitations to it. When you tell people in the vacuum, oh, quantum computers are massively parallel, and they are, in a sense. Mm-hmm. If you leave them alone and you don't try to measure them and you don't ask for, what's the output, yes, it's massively parallel. But the problem is, if you want to try to probe it and find out what is the output, it becomes classically not parallel. In other words, it'll collapse into one of its possible spectrum of answers, but you kind of destroy that whole superposition that was your calculating environment, if you want to think of it that way.
Okay, so it sounds like it's a little bit of a gamble in the sense that you can set up this quantum computer and you can let it run, and it may have the answer or it may not have the answer, but you don't know until you check it.
Absolutely.
And then when you check it, you're done. You broke your computer. And
you might not even be done in that sense. It might be wrong. In other words, you're
it's very powerful but not precise.
Yeah, that's. So think of it this way. You have this thing that's running in this nebulously, massively parallel way, and the things that make it run are physical processes. Maybe there are lasers that apply pulses to atoms that make atoms go through certain quantum mechanical duty cycles in their lives, whatever. The work I do is more related to manipulating photons, but it doesn't actually matter the physical system.
Right, any quantum system will do.
So if you have any kind of canonical two-state quantum system that has essentially a yes or a no to it, whether that's horizontal and vertical polarization, or yes, there's a photon here, or no, there's not, it doesn't matter. If you let that thing run in its nebulously, massively parallel way, you might imagine that in a loose sense, it cycles through all the possible answers it could ever get to a problem, starting with whatever initial condition you set up. Now, when you measure it, it might, or it probably even will, produce the answer to the problem you're trying to solve.
Right.
But like computers do, they don't care what problems we're trying to solve.
Right.
So it's possible that you could probe the system and you could measure an outcome that actually is not a physical answer to the problem that you're trying to model, let's say. No pun intended, but in parallel with the development of even classical computer science, but especially quantum computer science, is an entire area of research called quantum error correction, where folks have come up with very brilliant schemes for figuring out. So you make one quantum CPU and it might give you the right answer, that might give you the wrong answer. What folks have figured out roughly is if you make a few of them and you poll the answers, as long as you get the right answer something like a third of the time, then you can filter through the data, you can kind of process the data and identify which one is giving you the right answer.
So this is like polling the audience on Who Wants to Be a Millionaire?
Yeah.
Not everybody's going to be right, but you're going to be more right than wrong, and so you can use that.
We've known each other a long time, and we both know that each other has a significant amount of teaching experience at all levels. You ask your class a question, and the class is ideally filled with informed observers. Mm-hmm. In other words, they're to various levels informed on the topic that you're talking about. So if you ask them a question about something upon which they have this modicum of information, and you poll the class for the various answers they get, the basic idea is that statistically speaking, even if you don't get the right answer more than half the time, you're going to get more repetitions in right answers than you will in wrong answers.
Right.
Because wrong answers are, in a sense, statistically distributed.
Right.
So you might get 7 or 8 wrong answers that are all different from one another, and you might get 2 or 3 right answers, which will all be the same. And you can kind of leverage that to figure out, well, this is probably the right answer, and there are very sophisticated mathematical models for exactly how many right answers do you have to get to correct.
Right. So there's only one right answer. You always keep getting that. But then
that's right. Yeah.
When you're wrong in a diversity of ways.
Yeah. Right. So it's, you might be left, you might be right. You just, right. It's luck of the draw. I mean, I'm vastly oversimplifying. I don't even mean to market myself as an expert in error correction. Much to the chagrin of my PhD thesis advisor, who is, but one way you can correct for this idea that even if your computer works perfectly, it might produce the wrong answer. And
so it sounds like there's some power there, but you have to be really careful about constantly making mistakes. We can talk about in classical computers, for example, you can make mistakes in the code or something could glitch in the circuitry, but a perfectly coded quantum computer running perfectly would still have probabilistic errors.
Well, right, yeah. So because you have this wide array of possible outcomes.
Right.
In other words, you're taking advantage of this massively parallel computing ability, but you have to allow for the fact that introduces the idea that you could get maybe massively parallel outcome, and you might not want that outcome in every case.
So what are the big type of questions that quantum computing wants to address? I mean, there's a lot of talk about how quantum computers may revolutionize how we do things, or in encryption and things like that. Are there any particular problems that quantum computing really wants to go towards?
Quantum computing, as it developed historically, really comes out of an idea, I think, that Richard Feynman presented in the 80s and then kind of took off slowly, and about the mid-90s through the early 2000s really ramped up. And the reason why it really ramped up was because the actual algorithms that one would run on a quantum computer, many of the popular algorithms, were discovered far before anyone thought of an architecture where you could actually run the algorithms. In fact, it's kind of where we're at right now. I mean, there's not any real good architecture to run the quantum algorithms that people have worked out, and they've worked out very meticulously to account for these things like this idea of measuring the outcome and how do you actually extract information from your quantum computer. Other problems like decoherence. In other words, in quantum mechanics, the environment's a physical thing, so we don't necessarily get to decide when the computer gets measured. So if you have thermal fluctuations in the area, it might crash your computer.
Somebody shook it or jostled it, and all of a sudden, we're observed.
You look at it funny, and because when you look at it, you got to bounce photons off of it, and that all hell breaks loose then. There's the maybe even more fundamental issue of what sort of things might we use as qubits in the first place.
Right.
And there are lots of different varieties of things that have advantages and disadvantages. But long before any of this stuff became a subject of heavy research, like it is now, people developed algorithms that would be robust against all these things. So the algorithms kind of lead the technology, if you will. And so the most famous ones are Shor's factorization algorithm. If one had a quantum computer, you could factor very, very large numbers into their prime factors much more quickly than classical computers can.
And that's used for encryption.
Yeah, so all encryption, as I understand it, is basically based on the inability of computers to figure out the prime factors of a gigantic 100-digit number or something like this.
I think they call it a one-way hash. It's easy to multiply, but
so
difficult to do backwards.
Right, so you give me the prime factors, and I can easily multiply them together and give you the 100-digit number. But you give me the 100-digit number and say, what are the prime factors?
That's your final exam.
It's going to take me more than the age of the universe to figure that out.
Right.
Typically. And that's what you're betting on, because if you give me a 100-digit number, which, by the way, we give each other all the time, we're constantly throwing around our 100-digit numbers about, this is my password for Bank of America.
Right.
If I was on Bank of America. This is, here's my password for my work. So we're happy to share the 100-digit numbers with one another, because we know that each other can't factor them. Okay?
Right.
I mean, in fact, governments and militaries don't even mind if other governments and militaries discover their 100-digit numbers, because they figure everybody just has classical computers. It takes a horrendously long time to factor these things, and so far hasn't been broken.
It's easier to get a backdoor or something in the code than it is to actually crack that 100-digit number.
It's what folks call exponentially difficult to factor that number. In other words, the more digits you add to that number, the number of resources and processors and bits in a computer that you need to factor it goes up exponentially with the number of digits. Peter Shor discovered an algorithm that one could run on a quantum computer, and this was discovered probably in about 99 or 2000, so it's quite a while, whereby you could roughly factor numbers that go in polynomial time, or polynomial resources. So
if you doubled the number, you add another digit, you're just adding another unit of time to that rather than doubling it.
Yeah, something like that, right? Quantum computation, it's a beautifully simple idea. The quantum mechanics that goes into it is actually kind of simple, but it's something that really requires a multidisciplinary effort to try to make it actually happen. To gauge and determine under circumstances when it does happen, how well does it happen, and what can we do, if anything, to make it happen as well as possible under those circumstances.
So all that complexity then put into the solving of the problem.
Yeah, there's just so many facets. And the thing is that it's almost like a race, because the first person who gets any of these things to work is going to know everybody else's passwords within a few hours. Whether they'll use that for good or evil, I don't know.
But it will be used.
It's one of those things. It's like, for many reasons, there are lots of companies, businesses, countries, defense agencies interested in being the first entity to be able to do this sort of thing. The flip side of being able to break somebody else's code is trying to make a code of your own that's robust against somebody else trying to break it. So this whole notion of cryptography, quantum cryptography, that goes along with quantum computing and quantum information. It's an exciting field, and it's a wonderful application for things in quantum foundations, which is what my real interest is in physics.
You're listening to One Universe at a Time. I'm your host, Brian Koberlein. We've been talking with Dr. Ed Hach, Assistant Professor of Physics at RIT, about quantum computing. In the second half of our show, Dr. Hach will trade places with me and ask a few questions. He would like to know about the physical constants of the universe and whether they change over time.
I've read and heard certain things recently that suggest people have done experiments that imply that the physical constants, like, say, the speed of light, appear to be changing over long time scales. My question is basically, what's that all about, and sort of how do we know? I mean, how can we tell that?
Right. Well, when we talk about the physical constant, like the speed of light is one, the charge of an electron, the mass of a proton, things like that. We call them physical constants because they're values that we find experimentally. So in all of our theoretical models, everything is based upon, well, we assume the charge of electron is this. We assume the speed of light is constant, but we have to measure that experimentally. And so one of the ideas that comes up is, what would happen if you tweaked these constants? And sometimes we'll do this in classes. For example, we'll say, well, suppose the speed of light were only 100 meters per second and you were riding your bike. What would you see? What would it look like? And the world would be very different. Even though the laws of physics would be the same, those constants would be different, and then therefore what we would see would seem very different. The assumption is that these things are physical objects. They don't change. An electron is an electron is an electron, and so that's part of the reason why we call them physical constants. We know in some sense that things that we've assumed were constant actually weren't. It used to be that we thought space and time were kind of this constant background that never changed, and then Einstein went ahead and screwed that up, and now we've got relative time and space and general relativity and special relativity. So there's been speculative ideas on what would happen if those constants have changed. And we know, some of the interesting things. If you changed the charge of the electron, for example, atoms would be smaller because they would be more strongly attracted to the proton. If you change the gravitational constant, the gravity on Earth would be more for the same amount of mass, and that would change, the amount of light that the sun gives off because it would have stronger gravity. So you can speculate with all of these different things. So the question then becomes, is there any way in which you could tell whether these constants change?
In terms of even structural things, for example, let's say the vacuum Maxwell equations that predict how light travels in the first place. The speed of light shows up there as a natural component of the theory. Even if it weren't an empirical quantity, we would it would still pop up right there and sitting right where it should in the wave equation for the propagation speed. And so I wonder, what are the implications for that sort of thing? Or are there any noticeable implications of letting that thing slowly, parametrically drift over time?
There is. And in fact, the speed of light was one of those that some people have argued about, because early measurements of the speed of light were actually quite varied. And so until we got to laser measurements, where we could actually do laser interferometry and measure it very, very precisely, the official value of the speed of light has changed over time, and dramatically changed over time. We were limited in what we could measure. And so every now and then this comes up, and someone will argue that, well, the speed of light was different in the past, and they'll look at the official measurements and make some argument based upon that. And that's not really a good way of doing it. If you look at the measurement of speed of light, if you look at the earliest measurements of speed of light, they were using the distance to Jupiter. So one of the first ones was look at the rate at which the moons of Jupiter transit Jupiter, so the Galilean moons. And that depends upon Kepler's laws of planetary motion, which is like clockwork. It works very well. And then how far away we are. So if Jupiter was closer to us, we'd see it earlier than if it's farther away. Well, the problem with that is that it depends upon how far away Jupiter is, which at the time when they were doing these measurements wasn't known very well, and they were based on certain assumptions. So they would do these measurements, and they would make some assumptions about the distance to Jupiter, and they'd get these wildly different values. So the fact that you're getting wildly different values doesn't mean that the speed of light has changed, but rather it means that our measurements may have been off or something. What's interesting, though, is that you can actually use astronomy to look at physical constants over time, because one of the things that you'll see is if the speed of light changed but none of the other constants changed, then the spectra of atoms would shift, and they would shift in a specific way. What you can do is you don't have to measure the value over time, but you can measure the relative values of each other by looking at things like atomic line spectra or looking at the redshift of stars from different distances and stuff. And because when we look at distant objects, we can look at them over time. We're looking basically backwards in time because light takes time to travel. We can actually look at distant objects and compare the spectra of those objects to the same material, the spectra now.
You mean if you look at a distant object, you're looking at light that came from a long, long time ago.
Right.
And you can correct for the fact that there's also a redshift associated with that distance.
Right.
And kind of bring it into the reference frame, if you will, of a similar object that we see much closer, and we still see there's a spectral difference.
Right. So if you looked at a pattern of a spectra, the redshift would take a certain pattern. If you think of a UPC bar, it has a pattern of thin and dark lines, and that pattern's unique. And if you moved it to the left or to the right, it's still the same pattern. So in a redshift, if you have a Doppler effect because something's farther away, that pattern is shifted either towards the red or towards the blue, but typically towards the red, but the pattern stays the same.
Right.
Whereas if the speed of light changed, for example, that pattern would shift to be a different pattern. It would still be shifted towards the red, but the pattern of light and darks relative to each other would shift. Mm-hmm. And so we can look at distant nebula clouds. One of them was looking at clouds of alcohol. You look at alcohol light spectrum, and you compare them, from billions of light years away to ones now, and you see if they've changed. And what we found is, I think the best constraint we've got is no measurable change over 7 billion years, which means that the most it could have possibly changed would be 1 part in 10 million. Over 7 billion years. So for basically half the age of the universe, it's changed not at all as far as we can tell. So, and we've done this with things like the gravitational constant and the speed of light and the fundamental charge. And what we find is those, to the limits of what we can observe, haven't changed over billions of years.
So the fundamental charge is an interesting one to think about, at least for me. Suppose that one found a small change in the fundamental charge over billions of years. And you can suppose also that there are some electrons in the universe that were created billions of years ago, and some that maybe have been created more recently through physical processes. So in the sense of the Pauli exclusion principle, are they still identical particles?
Right. If they change over time, in fact, they wouldn't be. The idea that if the physical constants actually change, then basically all of our fundamental assumptions about physics would change. Like you're talking about, if an electron happened to appear, from matter-energy conversion early in the universe in the first billion years, if the charge was different then than now, then particles that appear now, electrons that appear now, would have a different charge, which goes against the very nature of what we see, which is that all electrons have the same charge. If the charge changed over time, we could actually determine the age of electrons or protons by looking at their charge and looking at how they vary over time. It would mean that if old electrons paired up with new protons, you wouldn't get an exact cancellation of the charge because they'd be different. And so you would have a net electrical charge to all material, which we don't see. So all of the evidence that we have points to absolutely no change.
Good.
I mean, it's interesting because it brings up another one where this idea of changing constants shows up is in something called the anthropic principle.
I think I know what this principle is. Probably can't say what I think of it on the radio, but
well, there's different types of anthropic principles. I mean, there's the kind of the non-controversial anthropic principle, which is the way we exist, that our physicality and our place in the universe is dependent upon the conditions of the universe as they've been historically over time, which isn't controversial at all. The idea that why do we appear now as opposed to earlier? Well, it takes billions of years for life to evolve, so we couldn't have appeared in the first 100,000 years of the universe. just because of the way evolution works. That's not really controversial. The more controversial take on it is the universe is specifically tweaked for living things like us to exist.
This is the one that I've heard.
Yes.
It seems kind of backwards to me.
Yeah, it is. It's very controversial because on the one hand, that argument can be useful in a theoretical sense of cosmology for why we have certain values. But it does seem, like trying to derive an equation, 2 + 2 is 4, then a miracle occurs, and therefore we get our solution. Because it's arguing that our existence then has an implication for the cosmology, which is not, it doesn't seem very scientific in that sense.
Well, it seems like using a constraint in reverse.
Right.
In other words, instead of applying a physical constraint to, say, the origins of the universe, you're applying a physical constraint to explain the way the universe is now, kind of ex post facto.
Right. It would be like taking a sample, and it's like, well, if I'll take a random sample of everyone around me, and I find that the vast majority of people I encounter at random speak English. Well, humans must speak English, which is completely unfounded because you're biased in your sample. Mm-hmm. And the argument against the anthropic principle is kind of the same in that we happen to be living organisms that exist in a universe with these physical constants. And to say then that, well, if the physical constants were different, we wouldn't be here. But the physical constants aren't different. The physical constants are what they are. It's hard to argue that our existence places any constraints on the physical constants. We've been talking with Dr. Ed Hach, an assistant professor of physics at the Rochester Institute of Technology. Our program is produced at RIT by Mark Gillespie with support from the RIT College of Science. I'm your host, Brian Koberlein. Thanks for listening to One Universe at a Time.